Right now, as you watch this, your bank is doing math, not big budget supercomputer math, simple multiplication. And that multiplication is the only thing standing between your savings account and anyone who wants to read it. The catch: a machine that doesn't fully exist yet could break that math in hours. This is RSA encryption, and this is why the whole internet is quietly panicking about quantum computers. Here is the core problem. Every time you see that little padlock in your browser, every HTTPS connection, every login, every bank transfer, it is protected by a cryptographic system called RSA. RSA has guarded the internet since 1977. It is elegant, it is battle-tested, and it is mathematically doomed the moment a sufficiently powerful quantum computer comes online. We are not there yet, but the clock is ticking, and the people who built the internet know it. So what actually is RSA? The whole system rests on one beautiful asymmetry. Multiplying two large prime numbers together is trivially easy, your laptop does it in a nanosecond. But if I give you the result and ask you to find the original two primes, that is a fundamentally different problem. For a 2048-bit RSA key, you are looking for two prime numbers, each roughly 617 decimal digits long. The fastest known classical algorithm would need millions of CPU years to crack a single key. That gap, nanoseconds to multiply, millennia to reverse, is the security. Your public key is the product. Your private key is the two primes. Share the product freely. Guard the primes with your life. Every time you visit your bank's website, RSA runs a precise 5-step dance called the TLS handshake. Your browser announces what encryption it supports. The server responds with its RSA public key, wrapped in a certificate signed by a trusted authority. Your browser generates a random secret number and encrypts it using the server's public key. Only someone with the matching private key can decrypt it. Both sides then use that shared secret to derive symmetric AES keys. From that point on, all your data flows through AES. RSA's job is done. It ran for a fraction of a second and established a tunnel that would take a classical computer longer than the age of the universe to break. That is the system. That is what is at risk. In 1994, a mathematician named Peter Shor published an algorithm that changes everything. On a classical computer, factoring a large number requires trying possibilities one by one, work that grows exponentially with key size. Shor's algorithm uses quantum superposition to essentially explore all possible factors simultaneously. The result, factoring a 2048-bit RSA key, drops from millions of CPU years to a few hours on a sufficiently powerful quantum machine. The hardware requirement is roughly 4,000 logical error-corrected qubits. IBM's latest processors have passed 1,000 physical qubits. The gap is closing. Most cryptographers estimate we have between 5 and 15 years before a cryptographically relevant quantum computer exists. That sounds like a long time. It is not. Here's why it is not a long time. The harvest now, decrypt later attack. Nation-state actors, and we know this because intelligence agencies have said so publicly, are already collecting encrypted internet traffic in bulk. They cannot read it today. They are storing it and waiting. The moment a quantum computer capable of breaking RSA exists, every gigabyte of data collected over the past decade becomes readable. Medical records, legal communications, classified government data. Anything encrypted with RSA before the migration is complete is retroactively exposed. The U.S. Cybersecurity and Infrastructure Security Agency put it bluntly in 2022. If your data needs to remain secret for more than 10 to 15 years, you need to start migrating to post-quantum cryptography right now. Good news is that the solution exists and it is standardized. After 6 years of evaluation, the National Institute of Standards and Technology finalized the first post-quantum cryptographic standards in August 2024. These algorithms do not rely on factoring. ML-KEM, based on CRYSTALS-Kyber, uses the hardness of problems in mathematical structures called module lattices, problems that Shor's algorithm does not help with at all. It replaces RSA and elliptic curve Diffie-Hellman for key exchange. ML-DSA, based on CRYSTALS-Dilithium, replaces RSA and ECDSA for digital signatures, the mechanism that proves a website certificate is genuine. SLHDSA, known as SBHINCS+, offers a conservative alternative based purely on hash functions which have been trusted for decades. These are not experimental proposals. They are published, peer-reviewed, government-mandated standards. The migration is already underway for those paying attention. Google Chrome added support for X25519 Kyber 768 hybrid key exchange. Cloudflare is running ML-KEM 768 in TLS connections. Apple rebuilt iMessage's encryption layer with a protocol called PQ3. Signal deployed PQXDH in 2023. The U.S. government has mandated that federal agencies complete their migration by 2030. The pattern across all of these is the same. Hybrid mode first, run the post-quantum algorithm alongside the classical one simultaneously, so you're protected against harvest attacks today while the ecosystem catches up. Then full migration as libraries, certificates, and hardware support matures. The hard part is not the cryptography. The hard part is inventory, finding every place in your systems where RSA lives, which is almost certainly more places than anyone documented. The deeper lesson here is not about RSA specifically. It is about cryptographic agility, building systems that can swap their underlying algorithms without requiring a complete rebuild. RSA is not broken today. Classical computers cannot crack it. But the internet spent 40 years baking RSA into everything from TLS to code signing to VPN authentication to hardware security modules, and now the industry is discovering how painful it is to change an assumption that was never designed to change. The right response to quantum computing is not panic. The math of RSA is still holding, but the right response is also not complacency. Post-quantum standards are finalized. Libraries are ready. Every month of delay is another month of encrypted traffic being harvested and stored. The question is not whether to migrate. The question is how fast you can move. Thanks for watching.